You ever hit one of those calculus problems that just feels, well, impossible? Where the function is so tangled up you can't even begin to solve for y? Well, today we're going to pull back the curtain on a super clever tool called implicit differentiation. It lets us find slopes and rates of change even when the variables are completely tied together in knots. It's pretty cool.
So let's start with something we all know, right? The explicit function. This is your classic, comfortable y equals f of x. You plug in an x and it spits out a y. Everything's super neat, totally orderly, and y is sitting all by itself on one side of the equation. Simple enough. But things get way more interesting when we look at an implicit function. See, on the left, y is the clear output, no problem. But on the right, you've got the equation of a circle, and now x and y are all mixed up. They're tangled together. There's no simple y equals something. So this raises a pretty big question. How in the world are you supposed to find the derivative of that?
And that really brings us to the central mystery we're trying to solve here. If you have a circle, which, let's be honest, doesn't pass the vertical line test and isn't a simple y equals f of x function, how do you find the exact slope of the tangent line at one specific point, like, say, 3, 4? It kind of feels like our normal tools just won't work.
This really gets us right into what I like to call the unfunction problem.
So to solve this, calculus hands us this procedure that, I gotta admit, feels a little bit like a magic trick at first. The steps, they work perfectly every single time, but it's not obvious why they work. So let's walk through the mechanics of the trick first, and then I promise we'll pull back the curtain and see what's really going on.
The whole process is really just 4 pretty straightforward steps. Think of it like a recipe. First, you're going to differentiate everything in sight with respect to x. And here's the key move. Every time you differentiate a term with a y in it, you have to remember to multiply by dy dx. That's the chain rule doing its thing. After that, it's just algebra. Gather all your dy dx terms on one side, factor it out, and solve for it. Okay, so let's try this with our circle. The derivative of x squared with respect to x, that's just 2x. Easy. The derivative of y squared is 2y, but wait, we just differentiated a y term, so we have to multiply by dy dx, and the derivative of a constant like 25 is of course 0. And boom, just like that, the dy dx term we've been looking for has appeared in our equation.
Now we just do the algebra. We move the 2x over to the other side, divide by 2y, and what we're left with is amazing. We now have this simple, elegant formula for the slope at any point on the circle. And notice, the slope depends on both the x and the y coordinates, which makes total sense for a circle, right?
So now we can finally answer our original question. We just plug in our point, 3, 4, into the formula we just found. So dy dx becomes -3 over 4, or -0.75. So yeah, the mechanical trick totally works. It gave us a real, concrete answer for the slope.
But hang on. This is where you should pause and get a little suspicious. I mean, okay, it works, but why? What did we actually just do? What does it even mean to take the derivative of an expression where x and y are all mixed up like that? This is where we get to the real beauty behind the whole thing. All right, let's pull back that curtain. Let's talk about how this thing really works. The key is to reframe the problem. An equation like x squared plus y squared equals 25 isn't just a description of a shape. Think of it more like a strict rule. A constraint. For any point xy to be allowed on the circle, it absolutely must obey this rule. No exceptions.
So just for a second, let's give a name to that expression on the left side. Let's call it s. Now, for any point x, y that's actually on our circle, the value of s isn't just 25, it is locked at 25. It absolutely cannot change.
Now, imagine we're standing at a point on the circle, and we decide to move just a tiny, tiny bit. We give x a little nudge, dx, and we give y a little nudge, dy. Well, this formula right here, which comes from multivariable calculus, tells us exactly how much the value of our s is going to change in response to those little nudges. And here it is. This is the big aha moment. If our tiny little nudge is supposed to keep us on the circle, then the total change in s, well, it has to be 0. It can't change at all. If s changes even by a tiny fraction, it means we've fallen off the curve and broken the rule. So if we force that change ds to be 0, we get this equation, 2x dx plus 2y dy equals 0. And just look at that. It's the exact same equation we got from our 4-step mechanical trick. This isn't magic. It's just the pure, simple logic of making sure we're following the rule. That's the why behind the how. Okay, that's pretty cool, right? We've got the how and the why. But let's zoom out and talk about why this tool actually matters, because it's a really big deal.
See, this whole idea unlocks a huge and powerful area of calculus called related rates. And you use this anytime you have a situation where a bunch of different quantities are all interconnected, and they're all changing over time.
The classic textbook example is a ladder sliding down a wall. You've got the ladder's height, y, its distance from the wall, x, and its length, l. The relationship is fixed. X squared plus y squared equals L squared. So, if we know how fast the top of the ladder is falling, that's dy dt, we can use this exact same technique to figure out precisely how fast the bottom is sliding away from the wall. That's dx dt. And this fundamental idea of interconnected systems pops up everywhere. In economics, you can model how a change in what people earn is related to market prices. In physics, you can describe how the temperature of a rising balloon is constrained by its volume. You can even use it in life sciences to figure out how a fish's brain weight evolved in relation to its body length over millions of years. They're all just interconnected systems following a rule. So the next time you see a complex system where everything seems to affect everything else, remember, this isn't just some weird math trick. It is a powerful lens for understanding the hidden rates and relationships that govern our world. It really makes you wonder, doesn't it? What other hidden relationships are out there just waiting for this tool to help us uncover them?